the winning team for track 2 here for the video action recognition. Yeah, cool. We can see your slides. Yeah, please start. Thank you.
Okay. Hello everyone, we are Team Efficient AI. In this presentation, we will introduce our technical solution for LPCV 2026 Track 2. The task is exercise action classification on the Qualcomm Snapdragon Edge platform, where both accuracy and low inference latency are required. Our solution consists of 3 stages. In phase 1, we trained a ResNet 18 R2 plus 1D baseline, achieving 88% accuracy, but quickly achieved a performance ceiling. In phase 2, we introduced a stronger slow-fast R101 teacher model, improving accuracy to 92%. In phase 3, we further enhanced the teacher with data augmentation, sampling alignment, data expansion, and hardcase mining, retrieving 97%. Finally, we distilled the teacher into a lightweight student model and applied quantization for efficient edge inference. In our initial experiments, we used ResNet 18 as the backbone of R2 plus 1D and achieving 88% accuracy. This showed that the baseline model had reasonable video recognition ability, but it was still insufficient for complex fitting actions. We then scaled the backbone to ResNet 15 and improved the accuracy to around 19%. This observation confirmed that model capacity was a key factor motivating us to introduce a stronger teacher model. Based on the previous observation, we select slow-fast R101 as our high-capacity teacher model. The slow-fast architecture captures both slow semantic information and fast motion dynamics, making it suitable for exercise action recognition. After introducing this, teacher accuracy improved from 99% to 92%. More importantly, it provides stronger and more reliable supervision for later student model distillation. Although slow-fast R101 significantly improved performance, our error analysis revealed 3 key issues. First, dark scenes or video with long lightning variance were difficult to classify. Second, video durance was inconsistent, and short video could fail to provide the required 16 frames. Third, the original dataset still contained ambiguous or difficult samples. Therefore, we improved the system from 3 aspects: environmental generations, temporal sampling alignment, and dataset expansion. To address lightning variance and dark scene failures, we applied correlated data augmentation. Specifically, we readily perturbed vision attributes such as brightness and contrast, allowing the model to observe the video under more diverse lighting conditions during training. This reduced the model's dependence on special recording environments and improved generation in real-text scenarios. The official set requires sampling 4 frames per second, with 16 frames in total. However, video durance vary significantly. For long video longer than 4 seconds, we sampled multi 4-second clips from different temporal segments to cover more action phases. For short videos shorter than 4 seconds, we use adaptive dense sampling by gradually increasing the sampling FPS from 4 to 5, 6, and so on, until 16 frames are obtained. This prevents short videos from being discordant and improves temporal consistency. To further improve data quality, we performed fine-grained segmentation on long videos from QVD benchmark. A long video may contain multi-action phases, and use only one course labels can introduce noise. We divided the long videos into shorter temporal segments and carefully assigned action labels to each segment. This increases the number of training samples while improving the label presence. In hard case minor, we first collected misclassified samples to build a bad case training set. For correctly classified samples, we sampled them with a probability of one-minded confidence, meaning that correctly predicted but uncertain samples were more likely to be selected. To prevent overfitting to only difficult cases, we also returned a pattern of easy cases. Finally, we construct a balanced return set containing both hard and easy samples. After phase 2 optimization, the teacher model retrieved 97% accuracy. However, slow VAX R101 has a high inference cost, with around 200 millisecond latency per inference, making it unsuitable for direct deployment on low-power edge hardware. However, the goal of phase therefore, the goal of phase 3 was to preserve high accuracy while significantly reduce latency. Our solution was to distill the teacher recognition ability into a lightweight ResNet 18 R2 plus 1D student model, followed by int8 quantization. During distillation, slow-fast R101 serves as a teacher model and provides high-quality prediction distribution and action recognition knowledge. The student model keeps the lightweight R2 plus 1D architecture, which is much more efficient for inference. Though distillation, the student learns not only from ground truth labels but also from the teacher's understanding of relationship between classes, allowing it to approach teacher level performance while remaining lightweight. Finally, we applied calibration-based int8 quantization on the student model. Quantization covers high% float point computation into a low-bit representation that is more suitable for edge hardware, reducing inference latency and computational cost. To minimize accuracy degradation, we used representation exercise samples for calibration to expand action ranges, allowing the quantization model to preserve strong recognition accuracy. That's all. Thank you.